This is problem number 6 from section 5.4. And in this problem, they want us to find the derivative for the following integral. So they give us an integral here, and they want us to actually find the derivative of this. Well, this comes back to the Fundamental Theorem of Calculus. So hopefully you've watched that YouTube video over the Fundamental Theorem of Calculus, because I'm going to use some of the steps that they use in that video to go through and evaluate this derivative of the integral. So first of all, let's define a couple things. When I use f of t in this equation, that's going to be my original function. And that f of t is going to be 1 over 1 plus t squared, because you can see that here that this is really 1 over 1 plus t squared dt. And you'll see me write that here in just a second. Now, if I take the integral, I'm going to write it as capital F of t. That will be the integrated function. All right, so I'm going to use f of t and capital F of t to represent my original function and my integrated function as I go. So the first thing I want to do is I want to rewrite this into a better form that's describing this this problem that I'm trying to solve. So first of all, if I want to take the derivative, I'm going to say that dy over dx is going to equal d over dx of this integral 0 to cotangent x of, and I like to write this as 1 over 1 plus t squared dt. Now you like to write this because I think that that's a little confusing, especially if you haven't done a lot of problems before, the dt being written in the top. And then I'm going to start to use, I'm going to start to define what f of t is. So my original function is 1 over 1 plus t squared, which I said earlier. So I write f of t equals 1 over 1 plus t squared, and then I can rewrite this as d over dx, the integral from 0 to cotangent x, f of t dt. Okay, so this is where I start to use this notation here. I'm going to actually do the integration. Well, the integration of f of t is just capital F of t, because that's what I define that as. So I'm going to say d over dx of, now I've done the integral of f of t from 0 to cotangent x. Okay, so I did the integral of f of t dt, and that was capital F of t, and I'm evaluating that from 0 to cotangent x. And I want to do the derivative of this. All right, so this is where all this notation comes together, and this is what they showed in that video. So that equals the derivative with respect to x. I now just plug in my cotangent x and my 0, so that's the integrated function with an input of cotangent x minus f of 0. Now I'm actually going to take the derivative of this. So this is the cool part. If I take the derivative of this, well, first of all, the derivative of f cotangent x just goes back to the original function. So I can write that as f with an input of cotangent x. But we know that this is the derivative of the outside function. I have an inside function, which is cotangent x. So it's not just, when I do the derivative of this function, it's not just f cotangent x, it's f cotangent x times the derivative of the inside. Well, what's the derivative of cotangent x? Well, if I bring in my my derivatives for trig functions, I can see cotangent x's derivative is negative cosecant squared x. So I can write this as times negative cosecant squared x. So the derivative of my integrated function f cotangent x is the original function cotangent x times the derivative of the inside, which is negative cosecant squared x. I got to use chain rule there. Now what's nice though is I do the derivative of f of 0. Well, f of 0 is just that's just a constant. So derivative of f of 0 is just going to be 0. So I don't have to write anything out here. I could say plus 0 if you wanted. And then I can go through and I can evaluate this farther. So f cotangent x, well, that's the original function, right, f of t, with an input of cotangent x. So I'm going to input cotangent x in for t there. So I can write that as 1 over 1 plus cotangent squared x times negative cosecant squared x. So that's negative cosecant squared x over 1 plus cotangent squared x. And then something awesome happens here. So if we come back to our Pythagorean identities, so I'm going to take out that integral. Let's look at the Pythagorean identities. We can see that 1 plus cotangent squared is cosecant squared. So 1 plus cotangent squared x here is actually cosecant squared x. So I can now write that as negative cosecant squared x over cosecant squared x. So these two things cancel, and I'm left with negative 1. So my derivative of the integral, of the original integral, so my derivative of this original integral is a negative 1.